Okay. All right, so what we're going to do is we're going to start with carbocation rearrangements. We'll see if we get to E2. If not, then that's what we're going to do on Friday. So you saw the carbocation rearrangements, the results of them on many of the problems as you were hopefully studying for Monday's exam. And the question is, what are they? They're going to be things that could happen in E1 or SN1. So give you some examples and we'll go over those. So in terms of, there's two names for these. These are either called carbocation rearrangements or they're also called hydride and methyl shifts. And technically they would be called 1,2 hydride and methyl shifts. The 1 and the 2 is just a relative numbering scheme. It means that the methyl or hydrogen is going to shift to the next position, which would be 1, 2. So let's look at different possibilities here. So let's say I had this molecule with the chlorine, and I said, let's react this with water. And from our chart, we know that this is a secondary system with a weak nucleophile, so its mechanism would be what's that? Just happened. Okay. There. It would be SN1 and E1. Let's just worry about the SN1 mechanism first. So, first step in the mechanism then is to do what? Form the carbocation by breaking the carbon-chlorine bond. And I'll show some transition states here. I'll show the new transition states. I won't show the old one. So we would get a carbocation plus a Cl minus. Now, the thing about carbocation rearrangements is I need to tell you when they occur. So I'm going to summarize with a bunch of rules. Rule number 1, I believe, is I need to tell you when to rearrange. Okay? Because otherwise you could rearrange everything. So in this mechanism, let's say I said my direction would be write the rearranged SN1 product. Then our first step would be to break the carbon-chlorine bond, and now we're going to rearrange. And here's what happens with a rearrangement. What happens with a rearrangement is basically my carbocation is an alpha carbon and we have 2 beta carbons. I can shift a hydrogen or a methyl group one position to form a more stable carbocation. That's going to be one of the rules, is we only rearrange to get a more stable carbocation. So if I take my hydrogen here and I basically move it as an H minus, meaning that it has a lone pair of electrons on it. If I move it as that, this hydrogen is going to pick up its pair of electrons and use it to bond to that carbon. The transition state for that is going to look like this. I'm going to have that hydrogen partially bonded to each of those 2 carbons, because that's the bond I'm breaking and the bond I'm making. And then I'm going to have that as my bond making, bond breaking part of the transition state. So the triangle, so it forms a triangle between those 2, Jacob.
They both have delta positive charges too,
Well, let's write the final product and then we'll go back in and we'll fill the charges. But you're right, they both will have a delta positive charge. So when I'm done then moving my hydrogen over there, what I'm going to end up with is I'm going to end up with a positive charge on that carbon. Because the hydrogen picked up both electrons as it moved. So that's going to leave that carbon with a plus charge. So a carbocation rearrangement means that I move the carbocation in one position, and it's usually the opposite. Well, it's always opposite in direction of how the hydrogen or methyl group goes. The group goes one way, the charge moves the other. So that means that this carbon would be slightly positive and this carbon would be slightly positive. So the plus charge is moving from the carbon that was attached to the chlorine, that was our alpha carbon, to now this carbon here, which will basically become our new alpha carbon if I was to do E1 on this. Okay. So it's a 1,2 hydride shift. Hydride is an H that's minus with 2 lone pairs. So that's why we call it a hydride shift, because it's moving as H minus.
There would be no delta minus on the H in the transition state?
Not really, because it doesn't have a formal charge in either the products. So it's just, it's if in effect moving that way, is why they call it a hydride. Because we don't call it like a methide, which would be a methyl with a negative charge. We just call it a methyl group. So it's always called a hydride shift. But it doesn't have a charge. The only charges are you got a plus charge here and a plus charge here. You got the 2 delta plus charges. Okay. So now, once we have this carbocation, now I can do my SN1 or my E1 or both. So now my water comes in. My water comes in and attacks that carbon, and in 2 steps, meaning the water adds, you lose the H+, I form my final product, which is that. So I form the alcohol out of that reaction. So this is an example of a hydrogen shift. So the purpose of this is to make a more stable carbocation. This shifting process, this transition state, I'm going to have to go over the transition state hill in order to get to the other valley. So a hydride shift costs you energy. You better make it up in forming a more stable carbocation, or the energetics just don't work out. So in other words, you can't go secondary to secondary. You certainly can't go secondary to primary, and you can't go tertiary to secondary. You've got to be going in a direction that gives you a more stable carbocation. Okay? So that's going to be one of the rules that I sum up with here. I need to tell you when to rearrange, and number 2, your shift has to give you a more stable carbocation. Rule number 3 is going to be that you only get one shift per reaction. So it's not like you can do this shift and the plus charge moves down the chain, and then there's another shift and another shift and another shift. No, you get one shift. There's not enough time for those multiple shifts because something's going to happen. A nucleophile is going to come in and add, or you're going to lose an H+ to form a double bond. So you only get one shift per mechanism. Okay. And the other rule is that for secondary and tertiary systems, and it's kind of hard to think of a tertiary system, because if you form a tertiary carbocation, how do you do a shift to get a more stable than a tertiary carbocation? That will happen, but next semester. Because you could say, but what about those benzylic carbocations that were in the book? Sure, that could happen. It could rearrange to form benzylic carbocation. But we're talking about that much more next semester. So a tertiary system isn't really going to be possible unless I can think of some sort of exception to that, which I can, but that's next semester as well. So I can't create a tertiary system that's going to shift. And if I did, I should save it for the next exam. But I can't think of one right off the top of my head. So it's going to be a secondary system. So secondary systems, what we do is we always take the secondary system, form the carbocation, and then shift. Now, what about a primary system? Can a primary system undergo a shift? Yes, it can. So let me show you what that mechanism is going to be, because that's going to be a little different, right? I still cannot write a primary carbocation, right? That's still not allowed. So let's take this system. So let's take an isobutyl chloride. And so in this isobutyl chloride, let's say that I want to form a carbocation out of it. Now, there are ways to form carbocations, some of which we'll talk about next semester, but I'll introduce them here. And then we'll react this with like water to undergo reaction. But can I form a carbocation out of this? The ways that I would use to form carbocations are, for instance, let's say I added silver plus to that. If I added silver to that, if the chloride could be removed by the silver, it would form silver chloride. And remember from general chem, the silver chloride's insoluble. So is silver bromide, so are all silver salts, except silver nitrate. So if I took this and I put it in water and I add some silver nitrate, it's a classic test to determine if you can form a carbocation. If you took a tertiary system, tertiary chloride, added silver to it, you would see almost immediately silver chloride precipitate. That indicates that the chloride came off, left the carbocation behind, and so it would be a tertiary system. If it took a few minutes, it would be secondary. If it never precipitated, it's a primary system. So this is a pretty standard test to make a carbocation, but also then to determine whether something's primary, secondary, or tertiary. There may be YouTube videos out there. There's YouTube videos on everything. But there might be some YouTube videos where people took primary, secondary, and tertiary halides and added silver to them, and you could see the precipitation. I'll have to look and see if I can find those. I know they're on a laser disc upstairs, but since most of you have never seen a laser disc, which was the upgrade from VHS, which you've never seen either, which was an upgrade from something else that I've never seen. I know the videos are out there, I just don't know if they've made their way from Laserdisc to YouTube. They probably have. But that's one way to make a carbocation. So I could do it that way. Another way that we can do it, if you we'll learn about in second semester, is that you can take either aluminum trichloride or iron trichloride, and what will happen is those ions, those metals, will actually rip the chlorine off to make FeCl4 minus and AlCl4 minus. And then, of course, up here we would just make AgCl, which would precipitate from solution. So there are ways to make carbocations. The aluminum and the iron are ways that we will learn next semester. But I'm going to show them now because I know for a fact that this rearrangement occurs. Some other ones I'm not quite sure of, but I know for a fact that this one occurs because when I taught at OU for 1 year, 1 year. Then I got this job, and I haven't been back since. But isobutyl chloride reacting with iron and aluminum trichloride did undergo a rearrangement. So that's one that I would say, yes, I know that's the case. So how does that work? And we don't need to worry about the metals. Let's just worry about the chloride coming off. I can't break the carbon-chlorine bond because I get a primary carbocation. I'm not allowed to write those. So what happens in a primary case? In a primary case, here's what happens. I'm just going to rewrite it here so I don't get confused with all the aluminum and silver. What happens in this case is the hydrogen shifts while the chloride is leaving. So this is a shift, leaving group leave, concerted one-step mechanism. And it has to occur this way because if it didn't, you would end up with a primary carbocation. So the transition state for this type of shift is again a triangle of the hydrogen to the carbon. And now a dotted line between the carbon and the chlorine so that the chloride bond is breaking. Okay. So that's our bond making and bond breaking scheme of our transition state. The final product that I'm going to get is now the carbocation moving to the tertiary position and the hydrogen moving to the primary position, and the chlorine gone. Now,
so are we saying that both of these things are like happening at once?
Yes.
Like the silver coming in.
If the silver was involved, the silver would be pulling the chlorine off as the hydrogen shifts, so that it never pulls the chlorine off to form a carbocation. And you could put a methyl group over here and it would do the same thing. So as the leaving group leaves, the shift has to occur, only just to avoid a primary carbocation. So in this case, the charges then would be, there would be a delta plus charge here, and there would be a delta minus charge on the carbon. There is no delta plus charge on the CH2. It would avoid that like the plague because it's primary. So there would never be any positive charge on the CH2. And then the hydrogen, again, is moving as a hydride, but there's no formal charge on it either. So this is how a primary system rearranges. It's this concerted shift, lose the leaving group, all in one step. Okay. Does this make sense? And then once you had the plus charge, you would do whatever you want with it. Add water, add alcohol, do an E1 once the shift is over. Now, what happened in this case was we weren't trying to do this reaction. I had grabbed isobutyl chloride from the shelf, and we were supposed to use tertiary chloride because tertiary chloride would easily have formed a tertiary carbocation. So about halfway through the lab, a young scholar comes up to me and says, "Hey, this bottle's isobutyl chloride. It's not tertiary. So do we have to start all over again?" And I said, "No, it'll give you the same product." And then they kind of pushed it a little bit more. "Well, I don't understand. How could it give me the same product? It's a different compound." And I'm like, "Well, we kind of learned about that in lecture." And then it continued, and I just said, "Okay, here's your post-lab question. Show me how this reaction would occur and refer to your lecture notes." And this is how it happened. So you could take either tertiary butyl chloride or isobutyl chloride, and you would get the same tertiary butyl carbocation. So this one I know works. Other ones, I kind of have to tell you that they would happen. And the reality of carbo-cation rearrangements is they're not, this one's 100%, but some of the other ones aren't. And if you do a rearrangement, you might get the same product, whether it's rearranged or not. So it's sometimes really difficult to see these carbocation rearrangements unless you set the system up and you look specifically for it. Okay, and all the carbocation stuff was done in the 60s. That was the heyday of carbocation chemistry. A guy named George Olaw won that when he was at Case. He studied all these carbocations. He didn't use iron and aluminum. That was well known before that, but he used some other ones to make all the carbocations and study them. And there are certain carbocations that never form. Carbocations have to be flat. So if you had a chloride, remember our friends, the bicyclic compounds that we just learned how to name? But if you put a chloride here, that chloride cannot leave. You go, but that's a tertiary carbon. It is, but the structure will never let the carbons become planar. And so that experiment of trying to make that a carbocation failed. And what happened was one of the hydrogens over here shifted over, or the methyl group shifted over, so that the carbocation ended up over on one of these two carbons and never on that. That's basically called Brett's rule, is that you can never have a carbocation on a bridgehead because it can never become flat. So there was tons of stuff. These were usually fluorines that antimony ripped off the fluorine. I remember finding a compound like this with a fluorine on it in the lab in graduate school that was hidden behind a whole bunch of stuff. I pulled it out. It was like, oh, it was from Germany, I believe. And it had a very famous chemist's letter on the inside to my boss saying, this is the world's supply of this compound. Can you test it and see whether it'll form a carbocation or not? And I showed it to him, and he goes, oh, well, I guess we never got around to that. So it was still the world's supply, but it didn't get used for what it was sent. And the best part was, send whatever you have left back. I said, you want to send it back to him? He goes, no, he's probably moved on. Should have saved the letter, though, because eventually this person will be a Nobel Prize winner. But so there's lots of issues with carbocations. These rearrangements can occur. And again, the rule here is, did I follow the rule? Yes. I went from potentially a primary system to a tertiary. Did I only shift once? Yes. That's it. Okay. So primary system shift, loose leaving group. So that's how we handle primaries, and that's how we handle secondary systems. Okay. All right. Is everybody kind of with me so far? Okay, so when would you have a methyl shift? Well, let me set the system up. Let me make it a little bit different here by adding one carbon, two carbons. So let's say I'm going to react this molecule with water. So secondary system, weak nucleophile, SN1 and E1. And I say, let's write the rearranged product for SN1. First step, I mean, at this point it's got to be getting pretty annoying. First step, break carbon-chlorine bond, make the carbocation. Then if I need to do a rearrangement, I need to look at the two carbons that are attached to the C+, which would be our beta carbons, or now our beta carbons, they'll change. And so now I'd say, well, okay, if I shift the hydrogen from this side, I'm going to end up moving the plus charge here. That's secondary. That's not helpful. If I move this methyl group, if I shift this methyl group over, I'm going to go methyl or secondary to primary. Definitely not going to do that. But what if I take one of these methyl groups and I shift it over where the CH3 takes a pair of electrons with it? The transition state is going to look like the other one, except now I've got a CH3. And so the methyl group's going to be shifting as part of that triangle, bond breaking, bond making. The plus charge is going to go from the CH, and this is just a CH. So it's going to go from the CH to the tertiary carbon. So that's my transition state. And then I'm going to end up with the plus charge here. And the methyl group shifted over. And so I'll end up with that carbocation.
I don't really understand how you decided to take that methyl versus the other.
Versus this one?
Yeah.
So let me do that. So if I took the methyl group on the right and I move it over here, I'll draw the bridge. So the methyl group's going to bridge between those two carbons. This is a CH. That's going to be a CH2. I guess I'm missing the CH2, CH3 there. So that's gonna, the CH2 is gonna come over, the CH3 is gonna come over there. I'm gonna end up with a delta plus charge and a delta plus charge in that transition state. And then I'm gonna end up with 3 methyls, the methyl group here, and a CH2 with the plus charge there. Good question. What's wrong with that? That is a primary carbocation. So this is a primary carbocation.
Those are bad.
Oh, they're very bad. They will never account to anything good, like points on an exam.
Oh, because we're looking at stability, right?
Right.
Okay.
So primary carbocations aren't stable because they only have one alkyl group. Remember, they have to have a minimum of 2. So yeah, no, it's bad. Next semester in lab, it'll be perfectly fine under certain circumstances. But in solution at room temperature, no. I mean, if you could form these things routinely, I think you would win a Nobel Prize. Because that's what happens when you do things that people say you can't do. But I wouldn't plan my career on it. Right? I think you'd probably be better off turning like straw into gold, like the old alchemists. No, or Rumpelstiltskin. I think it was Rumpelstiltskin that turned straw into gold. But it was based on alchemists that were trying to turn base metals into gold. Their careers didn't last very long. Because usually when the king found out they couldn't do it, they chopped their head off. But most of chemistry was actually developed around all those little tricks to turn base metals into gold. That's the foundation of chemistry. But I digress. So a primary carbocation isn't going to be stable, so we're just going to put a simple line through that. That pathway is not possible. And it's possible, it's just not high enough energy. We don't have enough energy to support that. So the whole idea here is that we have to, when we do our shift, go from secondary to something more stable. And primary is not more stable, the tertiary is. Okay. So now I have my tertiary carbocation, and then my water would come in, add to that carbocation, and then we would be in 2 steps. Again, we would form our final product. Again, water coming in, adding, losing the H+. So when you have a choice, you're going to move the carbocation to form the more stable. You're going to shift it to form the more stable carbocation. And so in this case, I can shift any of those 3 groups. Mary?
Okay, so it's not a matter of like the fact that you're shifting a hydrogen or a methyl group, it's just what you can shift to make it the most stable.
Exactly. So in this case, I have 3 methyl groups. I can't imagine a situation where you would shift a methyl group. The only way you're going to shift a methyl group and end up with a tertiary is if there's 2 other alkyl groups here. And later on, you could have potentially an ethyl shift, but we won't. We'll limit to hydrogen and methyl right now. Okay, so that's our rearrangements. So in terms of the rules here, the rules are here's the rules. So I don't write 2 sets of rules for the 2 different classes. So here is the rule number 1. I will tell you when to rearrange. Rule number 2 will be that you always rearrange to form the most stable carbocation, a more stable carbocation. And then rule number 3, you only get 1 rearrangement per reaction or per mechanism. You only get to do rearrangement once. And then our 2 different cases for a primary system versus a secondary system. The primary, you're going to shift and lose the leaving group at the same time. And you do that to avoid a primary carbocation. And then in a secondary, or if you can come up with a tertiary system, which I will next semester, I believe, then you lose the leaving group to form the carbocation, then you shift. So if we can form if we're in a secondary system and we can form the carbocation, we will always do that. And the alternative to that is to have a secondary and do the shift and lose the group, which sometimes people want to do in a secondary system. And then depends on the mood when I grade it, whether I'm just going to say, no, this really needs to be 2 steps, or whether I put an X with 2 steps and take some points off. So we usually lose and form the carbocation in the secondary system. The only time we shift and lose is primary. And that has a good reason, because I can't form a primary carbocation. And all of these are in a 1 mechanism. A 1 mechanism meaning that it goes through one mechanisms always go through as opposed to 2 mechanisms which don't. Jacob? 1 goes through a carbocation intermediate, 2 does not. It's okay. They looked at me the same way this morning. I'm like, one mechanism and nothing. So, and you're seeing that in lab this week, right? With the lab, if you're in lab, we're protonating the OH, and then the chloride or bromide's coming in and kicking off the water. We're doing an SN2 reaction, yet how many steps does it have? 2. But does it have a carbocation intermediate? I hope not, as you're writing your mechanisms. So the broader definition of 1 and 2 of unimolecular and bimolecular is carbocation 1, no carbocation 2. Oxonium, if that's all it is, it's a 2. Oxonium does not count as carbocation. And so anytime we undergo a carbocation rearrangement or a shift, it always results in a carbocation. It's always one mechanism. That's what that means. Okay. So, does that kind of make sense? So then, let's see. So then sound educational practice would tell me that I don't believe you when you say, yeah, it's okay. I give you a problem to do. So what I would like you to do is to write the major product or products, plural, of this reaction. You don't have to write the mechanism, just tell me what the products would be. And then, if you get more than one product, which one is the major product? Okay? So I'll give you a couple minutes. So I'll give you a couple minutes to do that, and then I'll ask for answers. We're just going to do SN1, not U1. We're just going to do substitution instead of elimination. So if you have elimination, that's fine. But I want to focus on these substitution products, or product, or whatever number of products you get. That's without rearrangement, right? Yeah. So now rearrange it and write those products. follow the rules. So your rearrangements have to follow the rules. Meaning you have to make a more stable carbocation. And you get one move, but you get one rearrangement, but if you had two possibilities, those would count as one move this way product, one move that way product. It's not two moves. That if you have more than one product, the question is now going to be, which one is the major product? Do we all have at least one product? I guess we'll have to find out. Okay, so first step in the mechanism. Form the carbocation by breaking the carbon-chlorine bond. We always miss that part. Okay, carbocation. We want to do rearrangement. So, if I put my hydrogens in, which hydrogen do you want to shift? Left one? Okay. We'll shift the left one over. That'll put the hydrogen where the plus charge is, the plus charge where the hydrogen was. And there's carbocation number 1. Is it more stable than the original one? Is that carbocation more stable than this one? Okay, valid shift. Anybody want to shift the hydrogen on the right? I do. Just to see what happens. So again, the hydrogen would shift to the left. The carbocation to the right. Should probably have asked with the one on the left, what kind of carbocation is this? Primary, secondary, tertiary? Tertiary. How about the carbocation I just made by shifting the right hydrogen? It's tertiary as well. Okay, so let's call this, valid. Good shift. Follows the rules. All right, we have A and we have B. And then we have C, both. And then we have D, don't know. So, my question is, which of these products is the major product? You can hold up fingers if you want, A, B, C, D. I didn't bring any extra cards. Plus, I'm kind of like out of cards. But okay, so your choices are A's major, B majors, both major. Don't know who's major. Okay? All right, particularly in the back, you might have to hold up really high. Okay. All right, let's see what we've got. We've got 10 A's, 2 B's, 4 B's. We've got 12 C's and just 1 don't know. Okay. So what's the major product? They're both tertiary. Does it matter what's attached to a tertiary carbocation in terms of the groups? Like, why would A be more stable than B or vice versa, Jacob?
Because it can disperse the charge throughout the ring on A, where it can't do that on B, which stabilizes it.
Now that's a cyclohexane ring, not a benzene ring. Do you wish to amend your remarks? I will totally agree with you. If it's a benzene ring, that's what would happen. Benzene ring with the double bonds. But this isn't a benzene ring. So how far can it go is the question. How far could the charge go? It's possible. Anybody want to go for B being more stable? So what we find is, and what we've said for stability of carbocations as well as stability of double bonds, that we're just counting alkyl groups. We're not counting what those alkyl groups are. So in this case, they're both tertiary. My standard line is, it doesn't matter whether they're methyl, ethyl, or a 100 carbon chain. They're all going to be the same. So the plus charge actually isn't going to make it too far in the ring. It's only going to make it to the two CH2 groups that are attached to it. So you could treat them as if ethyl groups, methyl groups, it's all the same. So tertiary carbocations, as far as we're concerned, have the same stability. Having 4 alkyl groups to a double bond, the double bonds all have the same stability, right? Because an alkyl group is an alkyl group. So our rule is we're going to treat alkyl groups the same regardless of what they are. So in this case, they're both the major product of the reaction. Why? Because they both carbocations have the same stability. Okay. So that's something that we want to keep in mind. Jacob?
Would steric hindrance ever come into play in something like this?
Remember that steric hindrance is a feature of SN2. So steric hindrance only plays a role in SN2, not in SN1. SN1, it's all about the stability of the intermediate, the stability of the carbocation. So that's something else that we have to make sure that we keep those terms in the proper places. So sterics never for SN1. SN1 always about carbocation stability.
Were you shifted the methyl group that's like attached to where the right hand is?
Which one do you want?
The methyl that's like attached to the carbocation.
That was just a chlorine. We only shifted hydrogens, we didn't shift methyls.
Like, could we have shifted the
That's a good question. I think if you, number one, you're not going to shift the ring. And you're not going to break up the ring to shift. One big word, yet. That can happen, but not now. If I shifted this methyl group over, here, what would happen is it would form a secondary carbocation. Remember, you got to shift to a more stable position. So that's something to always check out. But unless you're going to go to a tertiary from the secondary, you're not going to go. Too much energy. Okay? So let me just I will put this in the folder for this. This is going to be your problem for Monday. I'll just introduce it. You're going to take this molecule, and again, I will put it in the folder, and it's due on Monday. But I want you to write the mechanism, because this is another reaction that I do know what the products are, because we used to do this in lab a long time ago. If I take this alcohol and I react it with sulfuric acid, and I do an E1 reaction, I end up with 3 alkene products. And those 3 alkene products are both from rearrangement and also from just no rearrangement. So what I'd like you to do is to write the products from non-rearrangement and then write the products from the rearrangement. And there should be 3 unique products that you get from that. Okay, and so you're going to write the mechanism for each of those reactions. That will be due on Monday, so if there's questions, you can go ahead and ask. But I will put this in the folder as problem graded practice problem for Monday.
So are there
Rena?
6 mechanisms?
Um,
For rearranged and 3 for non-rearranged?
Some of the products come from both. So actually, if you think about, for E1, you only have 2 beta hydrogens to choose from each time. So you're going to form a mechanism to form the carbocation, then the 2 steps to give you the double bonds, then rearrange it, lose the hydrogens to give you the double bond again. So I don't think it's going to be 6. It's going to be closer to between 2 and 6. Okay. All right, if you have questions, email me. On Friday, E2.